quality systems, at least by research standards, that use the ideas that I've been presenting in both proof automation and a variety of other cool things you can do with Coq. There'll be a few other commonalities that'll probably become clear as I go. So mission 1 here is going to be to show a few examples of concepts I've discussed applied at scale. And mission number 2 is going to be addressing what the impression I've gotten talking to a few people about the basic idea of what is Coq and what do we do with it. And I think a lot of people have gotten the idea that roughly the following sentence describes what we do with Coq. We're going to build software as functional programs and prove the software correct. And then there are some things you can do afterward, like use extraction to translate to a bunch of popular functional programming languages. I'm going to take that sentence, we're going to write software as functional programs and prove it correct, and I'm going to show how we can relax all of the parts of that sentence, essentially except for the prove correct part, and show how it's very useful to do that in different examples. To try to get across the message, mechanized proof engine is a very versatile tool that we can use in many different ways. All right, so before I jump into that, one kind of administrative announcement. The code from my lecture yesterday is on our GitHub repository now. And on the web page for my lecture series at the summer school website, there's an exercise I'm suggesting for the session today. And it involves reasoning about linear equations over rational numbers and automatically doing drawing some conclusions from those using proof by reflection. All right, so I'll be presenting 3 different projects that in their different ways violate the assumptions in the sentence I just gave. And the first one will break the assumption that we're verifying functional programs, and you'll see more of this in Andrew's last lecture as well. This is a system called Bedrock. Is something wrong? Okay. And what it is, it's a platform for doing, I say, verified multi-language programming in Coq, where all the languages get compiled down to assembly and all the programs get linked together. And I'm just going to be demonstrating one particular C-like language in the Bedrock ecosystem here. And I'll start out with an example of a program that's supposed to add its 2 arguments together. Let me say a function that's supposed to add the arguments together. And this is the spec of that program. I'm using Coq's extensible notation system to let me write nice-looking specifications, as well as many other nice-looking things. And the spec here says it's a function that takes in the formal arguments n and m. It reserves no additional stack space. We do static reasoning about stack depth and whether we stay within limits. The precondition is just true. We take regular Coq props and put them in these funny brackets to turn them into props in the language that's being used here. And the postcondition binds the name r for the return value, which is asserted to be equal to the values of variables n and m when the function is called. So this v here is binding a name for a lookup function for the values of variables that we first enter the function. So this is a spec that says, please add 2 numbers. By the way, these numbers are all 32-bit bit vectors. They're not natural numbers as we've been mostly working with so far. They're not integers.
So these are notations for predicting and post-condition zone? Or I'm not sure.
These are a precondition and a postcondition.
Okay.
Does that answer your question? OK. This is a specification for a function. That's what the spec block introduces. Here's the function. It's inside a module that has the name add, and there's also a function named add inside with n and m as the arguments. Here's the spec, and we just return the result of this addition operation. So this looks like it should be a pretty easy one to prove correct. The function code looks almost identical to the specification. So let's prove it. Oof. So I call this automated prover of chaining together 2 tactics. Both of them work largely by evaluation in Galena. Especially the second one is using the proof by reflection style. It's doing symbolic evaluation in sort of a more scaled up version of what I used as my first example in my last lecture for the imp language, and doing some other kinds of proving with Galena that I'll talk about later. So here's our first example of a program specified, defined, and proved in Bedrock. But note, maybe it's a little hard to see at this point, it is not a functional program. It's more of a C-level imperative program. The pointers are coming soon. But any questions at this point? Yeah?
Modulo K is doing
Yes, modulo k means every function meets its spec. Yep.
And this demodule notation here?
I'm not sure. Is that a question?
Demodule in the definition thing.
That's not clearly a question.
What does it mean?
It's just delineating a program module.
Okay. And this notation has been defined somewhere else?
All the notations I'm using here for all my examples are defined in libraries that are not going to be on screen, but that we do rely on.
Okay.
Yeah, so it's pretty cool. You can embed almost any programming language inside of Calc with fairly natural syntax and then prove things about it. That's the big difference from the let's prove functional programs correct thing we've mostly been doing so far. We embed imp, and then CompCert embeds the syntax of C, but then we mostly, in our examples so far, focus on functional programs that manipulate these things. Well, the programs themselves in these embedded languages can be the main objects of our proofs if we want them to be, and that's what's happening here. All right, let's get a little fancier. Here's a specification for a swapping function. It takes in formal arguments x and y, and then we quantify over two unknown values v and w. The precondition says argument x is pointing to in memory value v, argument y is pointing to in memory value w. And these are separated by a star, which is an idea from separation logic, but I won't dwell on what it really means here. You can sort of think of it like an and that enforces lack of aliasing. And in the postcondition, it's the same except I swapped v and w between the two memory locations. How do we implement this? I'm going to use two temporary variables v and w, which get added to the, it looks like they're extra arguments of the function, but this is just the way you write extra local variables here. And we just read into two temporaries and then write them back in the other order. And we get that result. How do we know we get that result? Well, let's prove it. And drum roll, suspense. Yes, we did it. So this arrow with a star on the right is a memory read operation, and star on the left is a memory write. It's sort of related to syntactic intuitions you might have from writing C code. But it's an operator for the statement level, not the expression level here. It turns out that the language these are being written in is an extensible language. It isn't just one built-in type of syntax. You can add new kinds of syntax in a way I won't talk about in detail, but it all integrates with the proof machinery, so you can add new statements to the C-like language and add their proof rules, and then they automatically integrate into the automatic proving. Yeah?
I take it that you have eventually compiled down to some variant of like C-like and then use CompCert to get things?
No, but wait for the end of the file and you'll see how that works. All right. One more example. I'm going to work with singly linked lists, and here's a function that explains what is a singly linked list. This is going to be a function that's going to return a predicate kind of thing, a logical characterization of memory, and it takes as input a list of machine words. Capital W is machine word. This is basically the abstract version of the list, or the functional model, the spec version. And we're going to say what it means for this pointer P to be pointing to the root of a list that represents this mathematical list of machine words. So it's a recursive definition. Yeah?
I would ask the audience to make sure they understand this very well from Adam's description of it, because I'm going to be presenting essentially the same definition tomorrow for reasoning about C programs that manipulate like this.
Okay, but no pressure. Yeah.
Hprop is a type that you have that's sort of a prop, but inside.
It's a prop that's allowed to mention memory contents.
Okay.
Yeah, and then so there's this whole homotopy type theory thing that uses the same name. It started to be used about 10 years after it had this meaning somewhere else. Too late now to avoid that confusion, but this is not that. So, all right, what does it mean for a linked list to be in memory? Well, if we're trying to represent an empty list, then that just means the pointer P is 0. If we're trying to represent a non-empty list, then the pointer is not 0, and also there exists a tail pointer such that at the address P we find a two-element struct. At the first position we have the data value x that came out of the front of the list, And at the second position, we have the next pointer p prime. Furthermore, then in disjoint memory, we find the tail of the list, the tail pulled out of here, represented starting at the next pointer p prime. And I use %sep to set the so-called notation scope, so we interpret things like star as this funny conjunction instead of as multiplication.
Is the sep scope standing for separation logic?
It is. All right, so this is what linked lists mean. Any questions about this? Does this seem like what you think of when I say linked list? Notice that it enforces acyclicity because this operator doesn't allow aliasing between the two sides, and it therefore enforces finiteness and other properties that we usually expect by default, but sometimes don't think to write in our comments or other documentation. Now what I want to do is reverse a list in place.
Can I ask one more question?
Sure.
Did you say what the bracket bar notation?
I did. It's for injecting a prop into this other language of specifications.
And that prop can mention,
Whatever's in scope.
it's a plain prop.
Yeah. All right, so let's reverse a list in place. This is a function whose formal parameter is called x. It's going to need 3 additional stack slots, not implied by the spec without that annotation. Consider an arbitrary list, and imagine when you call the function, that list is pointed to by variable x. When we return with return value r, then that return value should be pointing to a list that represents the reverse of the original list ls. Here I'm just using the functional rev operation from the standard library that looks like this. Not too fancy. You might have seen this in the calc intensive at the beginning, maybe not, but it's a standard functional program. We're going to essentially show we're implementing this functional program with an imperative program in place. Yes?
How does the spec indicate that it's reversing in place?
Because all memory in the precondition needs to still be accounted for in the postcondition. And so maybe it doesn't quite say in place, but it says the old list is gone somehow. It at least says that much. Afterwards, you may only proceed using the reversed version. Okay. So here's a function for that. I'll give it more space and explain it incrementally. So a function is called rev. It has 3 local variables that aren't in the spec, an accumulator and 2 temporaries. We start out setting the accumulator to 0, and then I'm going to loop as long as the list x is not 0, and then a bunch of lines happen to deal with the fact that we don't have memory-to-memory transfers in this language. We break things down into more primitive steps, but basically, what do? We read from the data position, and this is reading the next pointer. Then this is overwriting the next pointer with the current accumulator, and then changing the accumulator to the original value of x at the start of this loop iteration. So maybe I'll draw a picture for this one, though it'll be a little shadowed by the projectors.
You can turn off the lights pretty easily.
Okay, I'll do that on demand if it seems important. These are just going to be some boxes here. So the usual thing that happens is when we're reversing a list, things look like this. Here's the head of the list, and we're going to walk down this successively, reversing all the pointers. Now here's the new head of it. That is what this code does. But we should prove it. Yes?
Assume that machine works 32 bits exactly because before?
It does assume that, yeah. All right. So I included a loop invariant here between these brackets that's going to help us do the proof. And loop invariants in Bedrock are a little unusual because they have both preconditions and postconditions. And that is not too important for this case. This is a relatively straightforward function, but it is the loop invariant is written that way anyway. So it says when we start a loop iteration, x is pointing to a list, and by the way, there's another list in accumulator for some other arbitrary value. They're both just quantified here. And then when we finally return from the function, it had better be the case that the return value is a list that we get by reversing ls and adding it to the beginning of ls. So there is some value here from having the post condition written like this. I think things would be a little more complicated if I could only write a traditional loop invariant where I don't get to change the post condition as I walk down the list. Or maybe I think I'd account for that in a different way. So now that code is accepted by the system. Any questions about this code, why it's correct, before we try to prove it formally? Yeah?
Are temp1 and temp2 in memory, or where are they?
You can just think of them as local variables in the usual way. They're not memory addresses that you can use as pointers. They're just additional local variables.
Okay, so they're not in the
Yeah. Yes.
What's the difference between arrow and star arrow notation?
With star on the right means memory read, star on the left means memory write.
And just plain arrow?
Just means assignment to a local variable. All right, so let's prove that this is the correct implementation of that. I'll start with the same proof from before. It's not going to turn out too well. The symbolic executor is going to get stuck, showing that this code avoids accessing memory addresses that it really shouldn't be touching. And we're going to need to teach the executor something about the behavior of this list predicate for it to make more progress. Yeah, bad result, Gold. This error message is not good. Something went wrong. And I happen to know the problem is, let's see, this memory read, for instance, is going to read from this location that the symbolic executor is not convinced is a legal memory location that's mapped into this program's address space. So to deal with that, we're going to need to teach the executor a new trick, and I'm going to grab it out of the definition of lists and prove a lemma. So this is the automation that's happening here is based on proof by reflection, but it's a kind of extensible proof by reflection that lets you plug in new lemmas when you prove them. So let me give one example. SLL, I think this needs to be list, let's say SLL non-empty forward. If I have a list and a pointer, and the pointer is not 0, let me make clear this is a word, not just a natural number, and I have an instance of this predicate, what does that imply? It implies sort of this, where I'll say there exist x and ls prime such that the list equals those together, and we already know p is not 0. And by the way, there also exists p prime such that this holds. So this is just sort of a restatement of part of the definition of SLL. And I can prove this by case analysis on the list with a tactic called sep lemma that automates the rest of the proving. And now I'm going to make some hints to feed to the system. It's called a tactic package. And I'll say, prepare the following hint list. Whatever I called this thing is in the list. So we distinguish between forward and backward direction hints. This one's forward because it's an implication where on the left is a use of a predicate we've defined. We'll also have backward hints where on the left on the right is the use of the predicate we've defined. Now I can do things a little differently. I'll just pass my hints as the argument to that tactic. And we should hope to make a little more progress this time, because now when we get to the point of reading here, we will see that this address is actually in scope, because that lemma will be used to break a list up into a known con cell and the rest. And we'll see that the memory access happens in the known con cell and is therefore okay. It's not going out of bounds. It's not touching someone else's memory that we weren't supposed to have anything to do with. I forget how long this is supposed to take. Any questions in the meantime? Yeah? Oh, okay. I'll take the question anyway.
Can you show the definitions of LS and SLL again? What they were.
LS is just the list of words that we're representing. Those are the list of data values for the list. It's the functional version of what we're representing imperatively in a manner explained by this predicate.
So implicitly, there's a chunk of heap behind all of this, and
Right. An imperative linked list is a not necessarily adjacent subset of the main memory that we pull off and say, look, it's a list because the pointers follow this pattern.
And then LS is just Cox's list?
Yes. LS is a normal functional list. The same kind from Software Foundations and many other Coq sources. All right, so now we're left with something we should do here. This is probably not the right one to look at. Where do we see an example of what we're stuck on? Let's look for an SLL here. Here's a good one. Here we have a post condition. So let me explain what these goals are. I was looking at 3, I think. HIMP is implication on these HProp specifications, and we need to show that this predicate implies this predicate, where in the end we have a linked list that is whose data part can be described with a cons operation, and here's the root pointer. So this is the right-hand side of the implication. On the left-hand side, we see, oh, we seem to be in luck because the pointer points to data value x7. Good, we needed x7 right here, and the memory location 4 words, 4 bytes after the head pointer points to the accumulator, and then the accumulator continues with the list x1. Good, that's what we needed next. But Coq isn't proving this for us next. So I mentioned both forward and backward hints, and this is where we're going to use a backward hint. So I'm going to go up and use some copying and pasting to very efficiently prove a backward hint by copying the right-hand side and putting it on the left. And with proving this fact, we'll essentially be showing logical equivalence of the two sides of the implication, whereas we had only one direction before. I'm going to call this backward now. And we're just stuck with this case where I have to use this known equality between two conses, which I can handle with match and goal, look for any sort of cons equality, and then use inversion on that, and then sep lemma. All right, so now I have a backward direction of the same property. Let's put that into our hint database and then see where we get with that in place. Another and quite intentionally injected question period here. Yes?
So how does the automation know that it shouldn't get too about folding and unfolding according to these standards?
So each one of these is guarded by the fact that the pointer is non-null, and it just doesn't happen that when you introduce new pointers through symbolic manipulation, we know the new ones a priori are non-null, so it won't fire for those. Yeah?
Looks like you're building a hint database directly into Galena instead of LTAC.
Right.
Can you talk more about why you did that or how it works?
The main reason is performance, and it works by reifying the syntax of lemmas into a type of abstract syntax tree as an inductive definition. And there's a paper about it. It's hard to explain quickly.
You'll post a link to the paper?
Interesting question. If you go to the Bedrock, if you search for Bedrock, it's probably not hard to find, but I could try to do that. I might wind up mentioning enough parts that all the papers about Bedrock are relevant, so I'll consider creating some sort of curated list of papers for particular subjects to follow up on. So let's see where we're stuck now. What other implications could Coq not prove? That's probably a good one in the third position. What do we need to show here? We're trying to show this implication between a list that has an x and a list that has x0 reversed and put onto x1. So we want to put these two lists together and show it's the same as this one. By the way, we know that the pointer x is null. So what does that mean about this list whose root pointer is the value of x? Could we simplify this expression knowing that this pointer, that's the root of a linked list, is actually null or 0? Yeah, the list is empty. We should just be able to cross this out and additionally record the fact that x0 must be nil. So given the steps I've been taking so far to refine this proof. Any suggestions what we would add to our tactics to take advantage of that empty lists go away property?
Simplify will not do this on its own.
Simplify will not do this on its own. Or simple won't. Yeah.
You build a forward hint more or less that says if you have the fact that some pointer is null, you the variable is actually like related to the empty list.
And additionally, there's no memory being taken up. Those are the two facts we need, right? So let's put that into hint form. So I'll make a forward proof of this. Oops. Forward proof. SLL empty forward when the pointer actually was 0. Then what happened? Well, we learned the list was nil. And implicitly, by having nothing else on the right-hand side of the implication, a pure fact like this takes up no memory. So we're implicitly saying this list took up no memory all along by not including anything else over there. And the same proof works for that. You might also guess at this point, you might as well do the backward direction. We'll probably need that. And that is true, so let's do the backward direction. Okay, so I'll put those into my hint database. When I run this, prepare is a tactic that's taking all these different lemmas and reifying their syntax into a calc AST of lemma syntax and then putting everything together in a form that later tactics will be able to do good things with. So let's see what happens next. All right, we come to another entirely intentionally placed question period. Anything anyone wants to ask here? What's the grouping for prepare? Doesn't matter. You build things in tuples however you want, and the tactic recurses through tuple structure. Yeah?
A follow-up on that is you've chosen to group the forward and the backward together, so that was arbitrary?
Forward and backward hints are used in different ways in the algorithm.
Right, but so how is prepare, I was assuming that the grouping was indicating that the first two were forward and the final two passing were backward.
That's right.
Okay.
Oh, we made some progress. In fact, there's now one subgoal left. So we're almost there. What do we need to prove? I have a linked list that arises by reversing x0 and putting it onto nil. And I really wish it was just reversing x0. But the root pointers are the same between these two cases. So what do you think we should try to add to get this proof to go through?
Well, there's a theorem about rev and rev append.
Yeah, we don't have to work too hard to remember it. Let's just ask Hawk, hey, listen, I have a rev and a rev append. How does that make you feel? And it says, oh, it makes me feel like this. It says rev append L nil is equal to rev. That looks good. So let's do this. Hint rewrite right to left direction. And this goes into the SEP formula database. And then this should all finish now. Let's see if it does.
Put in a deliberate question period here.
Yes.
Question about the question period. Why did you choose to make the question period so long?
I think a bunch of people in France chose to make it so long. Yes.
So since you're reasoning about stack space explicitly,
Uh-huh.
does this mean that you're not getting any sort of register allocation? You're more or less like things that you choose to be in stack are in stack, and things that you choose to be in locals are actual registers?
There are no registers there are no long-lived registers in the particular code compilation strategy here, except for the stack pointer. All right, program's correct. We can all rest easy now. Any questions about the proofs before I show the compilation, which would partly answer that question, how are registers used? All right, let's compile some code. Oh, yep.
Just a quick question. So does this technique scale up to also like a circular register?
Circular list, probably. I don't remember if we did that concrete example, but it should. You can always drop down to manual LTAC proofs if you need to. So that sort of means if you work hard enough, you can prove all sorts of things. The question is, how does the automation help you on which examples? It would do most of the work for that example, I think. maybe not all. Yes?
Any chances that it works on 8.6?
No chances. Yeah, I'm running Calc 8.4 here. Yeah?
What is the fact and most effect on the DeepSpec? Is it the length of the code?
You're asking what is the function from the input to a good prediction of running time for the automation. I don't know. There are a lot of really avoidable algorithmic problems with the Calc kernel and the tactic engine that we're working on with INRIA. There's no fundamental reason this should be noticeably slow, and we're working with INRIA to make it faster. Yeah.
Can you elaborate a little bit on how you use hint databases? How do you separate lemmas?
So with the forward and backward lemmas, whenever you have an implication with the use of a predicate on the left, you try all the forward lemmas. And if the use of predicate is on the right of the implication, you try all the backward lemmas. Is that the answer?
No, I meant like in a more general sense of development.
I don't know if I have a more general answer ready. You generally have a different kind of pseudocode in mind for proof automation for each domain, and you think about what are the parts in the pseudocode that need to be told to behave a little differently for each program, and then each part like that gets a different kind of hint. Yeah.
So this is going to be in the repository, but this will not run on 8.
It's not going to be in the repository. I'm only showing examples that are already in the tutorial subdirectories of the open source released versions of these systems.
Oh, okay. So if we want to play with it more, we'll have to see from that.
Correct. It's not hard to find them. There are links from the DeepSpec summer school website. All right, compile time. Oh, one more. Yeah.
I have kind of high-level question. So you embedded this language inside Calc,
Yep.
and you embedded some kind of proof language on top of it, also inside the Calc. Is there any kind of practical application for this language?
I think wait for the next part that I'm showing.
All right.
So let's generate AMD64 assembly code from these programs. It turns out the original programs are actually basically notation for generating assembly code. So we can just run them and then do a little of extra assembly that I put in here. So here's the add program computed down to assembly code. All the constants are, the numeric constants are in binary because that's easiest to output. And yeah, you know, it's an assembly program. And it's very easy to add tooling to pretty print this to a .s file and then compile it and run it. So swap program, that exists too. There it is. And same for the reverse program, probably the longest one out of these. And we have other pretty printers for different assembly languages, like 32-bit x86 and ARM and so forth. So that might be an answer to the last question. This is a real way to make code that runs, and then you know it's correct. Yeah.
So you just said that the semantics of this Bedrock language are based more or less on assembly code. My understanding, my very shallow understanding, is that assembly code has fairly weird semantics.
Not for well-behaved subsets, usually. They're
Okay.
not, they're maybe verbose, but not necessarily weird.
That may be the answer to my question.
Okay, over there.
Is the AMD64 generation assembly, is that part of Bedrock, or is that?
It's part of Bedrock.
And is the compilation, I assume, to the assembly is verified as well, right?
It's not.
Okay.
It's not very interesting. Maybe someday we might verify it. Yeah.
How tunable is the exact assembly that you generate?
Very predictable from the Bedrock IL code that you produce in Calc. This isn't designed to get every last constant factor bit of performance, but asymptotically, it's very easy to tell what you're getting into. All right, I think I'm going to switch to demoing a different system now, unless there are any last questions on this one. Yes?
So how big is the program you're working on this
In terms of the lines of code and the notation I've been using to program here, probably about 1,000. Yeah, we use it to build a web server, running dynamic applications, and prove things about all of it, and some other places too. Yeah.
What are the constraints on the stack size that are like enforced by the logic? Like, for instance, could you do recursive functions that have unbounded stack size?
This language that I've been using doesn't support recursion. We have at least one other embedded language that does. Yeah.
Based on your class, based on how you mentioned web server, does the language support concurrency?
Doesn't support hardware multi-threading, but you can, of course, do things the way we did before we had multi-cores for concurrency, and that's what the web server does. It includes a cooperative thread library. All right, changing mode here. Let's, okay, so I said I was going to talk about how you might get the wrong impression if you thought, what do we do with Coq? We're going to write software as functional programs and prove them correct. So here's an example where we don't do the functional part, and now let's take out the software part and verify some hardware programs. So Kami is our framework for doing that. The first paper about Kami will appear at ICFP in a few weeks. And here's a kind of sneak preview. Oops, I need to change Coq versions. Actually, 8.5. While that's running. So Kami is going to let us write embedded programs in a different language, and now they're going to be compiling down to Verilog instead of assembly. And we're going to prove that they meet natural specifications. And we have implementations of multi-core processors and other such things in this framework, but I'll be sticking to simpler examples here. Let's try this. That's weird. Did that not finish in time? That was working before. Why is it not working now? Interesting. Quick check to see if there's an easy fix here. I have 8.5. I thought I meant to do that. Try what? But that takes too long to finish interactively. I think I won't run through this one interactively, but I'll just show you the code. Let's see. Here's an example of a Kami module. It might remind you a lot of what we've just seen with Bedrock. But this is all designed to be compiled to hardware. And so we only have finite data types. You don't have loops or recursion. All the effects of those we get by running across multiple clock cycles with single steps that follow in the fragment of code we see here. But Kami is based on the BlueSpec hardware description language, which is a much higher level than Verilog or VHDL. Allows you to define modules that contain private state, like registers. That part's not too different from Verilog. But then we have, within modules, rules, which are bits of logic that the language guarantees appear to run atomically with no interruption by other threads interleaving with them. And then the compiler to circuits figures out how to interleave these rules in safe ways that produce the same visible behavior as if they really were running atomically by themselves in some order. So this is a simple producer-consumer example that it has a private register called data that is an 8-bit word. And we read from that register and then call a method in another module to enqueue the data into a queue somewhere, and then write back to our data register a value 1 higher. And I've also included a method here that lets us overwrite the value of data with whatever we want. So this is basically a module. You can set data to get it started, and afterwards it's going to keep running forever. As long as there's space in the queue, it tries to push the next higher number in a sequence onto the queue. Since it's hardware, the queues will always be they will be finite capacity in practice, and the enqueue call will not be able to run when there's not capacity left. So let me show you another example. This is going to be a 3-stage pipeline that uses queues to communicate between stages. and maybe I'll draw that pipeline here. So input comes in one. Maybe it just came loose or something.
Yeah.
Or maybe it just added 1 minute of charge while sitting in there, and it'll turn off in a moment. Yeah. So let's see. It's a pipeline where data values pop in through queue on this end, and we add 1 and forward them to the next stage. And I think I'm going to multiply by 2 in the following stage. Yeah. Okay. I don't think there's any way to continue with the microphone, as far as I can tell. No, this is still on.
No, it dropped out for just a second.
Oh, okay. Well, all right.
It's okay.
Yep. So it's a queue of stages that are, we have 3 different processing components where each of them has input and output queues, and values flow through. The first stage involves incrementing by 1 before enqueuing in the next stage. And then after that, we'll multiply by 2 before enqueuing in the next stage. So the overall result is add 1 and multiply by 2. And we can write code like this, which says we have 1 data register. 1 execution step is to read from it, enqueue it in the next stage's queue, and then write back 1 higher. So it's not quite what I've written there, but that's like the local state change rule. And the second stage that reads, doubles, and enqueues. And then a third stage that dequeues from the second queue, has a local accumulator. Oh, so this is completely different than I drew, but that's one example of a pipeline. And then adds the current accumulator value to what it just read, and then sends the result of that addition off on the final queue. And then it replaces its own accumulator with this new addition that it did. So we have these 3 stages that we might want to break into 3 separate components that can run in parallel with each other for performance. This is sort of an idealization of a very important technique in hardware processor implementation. And then what we can do is we can actually create 2 concrete queues using a library module, and then compose all these stages together. Kami has a concept of module where you can compose 2 modules to create a larger composite module. So we do that, put all the stages together with the queues between them. And then we want to prove that together they implement this spec, which is just a single rule with 2 registers, data, and accumulator that effectively has inlined all the stages together, all the points where we enqueue somewhere and wait for someone else to dequeue it and compute. We just smush those together into 1 atomic block of logic here that does all the times 2s and plus 1s and additions as appropriate. And we'd like to prove that the composition of all those other modules is actually a correct implementation of what we see here. Yeah?
What is the semantics of the let declarations of the rules?
It's just assigning to a local variable, or equivalently, same as OCaml.
So what would that translate to at the hardware level? Like the registers will translate to registers.
It translates into another set of wires that get their values set by a circuit. So there are a bunch of well-formedness proofs we have to do to make all this go through, but I won't dwell on those. They're all easy to automate. And then we have this theorem we're aiming towards to prove that the implementation implements the spec. Our definition of that is any module in Kami has a set of traces that it might generate. Traces consist of both incoming method calls on the methods of your code and any outgoing method calls you send to other modules. And a given program implies a set of feasible traces when we assume other modules can call us however they like. So it'll in general be an infinite set of traces. And this correctness notion is what's called refinement, which we've seen in CompCert and other settings. And it basically means the set of possible traces for the implementation is contained in the set of possible traces for the spec. So the implementation cannot do anything that the spec could not also do. So there's one interesting trick that happens here. The first stage of our successive refinements where we'll keep taking the implementation and gradually transforming it until it looks like the spec. The first thing we do is take one of the FIFOs or queues and replace it with a so-called native simple FIFO, and I'll show you the code for that. It's not compilable code. It doesn't look like hardware anymore. It's just a spec level device. So if I look in Kami, and then where's native FIFO, then this is a FIFO whose register actually just holds a COC list. And this is crazy, right? We're thinking about building hardware. One of the registers is holding a COC list. It's an unbounded size thing. It's written directly in a functional programming language. We can't compile this in a straightforward way to hardware. But this is just a specification device. As we imagine the process of transforming our implementation towards the spec, we'll be gradually replacing hardware-y things with nice functional programming things until everything's nice. And then we did the proof. And so this is a queue that works by maintaining a COC list as a register. And we can see the code for NQ and DQ. For instance, NQ will just call a COC function, list NQ, that merely concatenates to the end of the list. That's something that we can't do directly in hardware, but this is sort of the spec. How is a queue supposed to behave? It's supposed to behave as if it had a true COC list inside of it, and it's allowed to refuse to run certain operations when it's run out of capacity. But whenever it does run operations, it needs to do so in a way that's compatible with our view of a queue as encapsulating a COC functional list. So we make this first transformation, and we can do a proof here using a transitivity tactic to prove that the implementation refines the one where we've changed one of the FIFOs into a native FIFO. And there's a short sequence of tactics that makes that work. We have to define an invariant that characterizes how to relate the state of our fancy pipeline to the simple spec. I won't dwell on the details of that. But somewhere we write down that invariant, and we prove the key rule for how it's preserved by a state change in the system. Here is another intermediate program where we're now focusing on just the first two stages. We're going to prove they can be collapsed into one that contains the combined logic of the two. In particular, here's that combined version that has both multiplying by 2 and adding 1 in a single rule that runs atomically. And we have a proof of it coming up down here. It relies on the invariant we defined, and eventually we're able to prove this fact that the implementation of the first two stages refines the version where the two stages are smushed together into one. And there are a bunch of tactics here, but not too many. There's a lot of automation lurking here, including, by the way, symbolic execution of these hardware programs using reflection, like we saw in my last lecture. And then finally, we need to merge. So we merge the first two stages. We can now pretend they're one. We need to repeat this and merge the combined first two stages with the third stage, and then we'll be finished. So the rest is sort of highly reminiscent of the earlier stages. Let's just take that for granted. And then we get down to the point of finally being able to prove the the original implementation, refines the original spec with a lot of transitivity and a lot of uses of algebraic properties of this plus plus operator for composing modules. And then at the end, we can actually generate some BlueSpec code from these designs. This code is actually very close to the syntax of the BlueSpec hardware description language to begin with. So that's not surprising that we can do it. Then we can feed that into a standard hardware synthesis pipeline and produce Verilog code that we run in FPGAs, or in theory, we should be able to create actual silicon from this, though we have not tried it yet. Yeah.
Going through BlueSpec, so that implies you have a BlueSpec semantics?
At the moment, the compiler is not proved correct, but that's in the to-do list. Yes?
Do you find that the tactics that you came up with for the hardware verification are different from the ones that the style that you use for functional program verification? If so, how?
Yeah, they're very similar at a high level, but there are interesting differences, like how we're used to in calc proofs writing simple and to get all sorts of algebraic things to happen automatically, and that doesn't work the same way for hardware designs. We don't have recursive functions, which are the main things that are getting simple by simple. And instead, key operations are inlining two modules together, where you wrote it as a module composition and you want to take all their registers and put them together in one place and combine all their rules and take every method call from one module to the other and replace it with its definition. That's sort of the equivalent of simple, and that's what we define that really gets run in a similar point in the proof to where you would run simple in a functional program software proof. And instead of induction, you have simulation proofs. So we're sort of defining slightly different but familiar versions of tactics for software proofs and making them work in this hardware setting. Yeah?
Out of curiosity, did you take any inspiration from, or compare this with Chisel and Clash, which are trying to make a more functional language for specifying hardware? Did you take some inspiration and abstractions, or
No, probably not. I don't know enough about Clash to even comment on it, but Chisel is a very low-level language compared to this one. You write Scala programs that generate very low-level circuits. And whereas in BlueSpec and Kami, you're writing calc programs that generate rather high-level descriptions, which are much nicer for proofs. I don't think Chisel is going to be practical for verification to the same extent that Kami is. Other questions about this one? Because of my strange calc versioning problem, I can't actually run this code that would generate a beautiful BlueSpec source file, but actually I think it's already cached here, so I can at least show you what came out when I ran this before. Kami ext, okay, well, target, no, not that one. Well, it did generate this big extracted ML file, but that's not very useful. This file computes the source code of the BlueSpec. It is not itself the BlueSpec source code. Did I put that in here? Maybe it's not actually.
The compiler generates a program that generates the BlueSpec.
No, calc extraction generates the program that generates the BlueSpec. Okay. We are just computing the BlueSpec in calc, but calc computation is slow compared to OCaml computation.
So extract OCaml, run the OCaml program, and the effect of the OCaml. And it's not that you're generating an OCaml program that turns every one of you generate an OCaml program for that particular piece of hardware.
Yeah.
Have you actually gotten hardware studying? Have you ever actually run things off of FPGAs?
Yeah.
This pipeline?
Yeah, we can run multi-core RISC-V programs that do citing things with locks and so on. Yeah.
How is the semantics defined? Is it defined like concert, the relation between state, or is it defined as a interpreter, executor function? Or?
It's an operational semantics, a small step semantics, where a step corresponds to one cycle of the hardware.
Okay.
I didn't see a link to like GitHub or something for Kami.
Oh, yeah. We haven't added the link yet. We should probably do that. You might be able to find it with the right search without too much work. I'm not sure. It is publicly released with an open source license. We haven't added pointers in all the places we should probably. It's associated with a conference paper that wasn't published yet, so soon it will. The paper itself contains a link. Any other questions on this part? All right, so let's review which of the parts of using Calc we've debunked that people might assume are fundamental. So we're not always writing software, and when we do write software, we're not always writing functional programs. And the last part of the recipe I gave that I said I would quibble with is we're going to write the code and then we're going to prove it. Let's not do that. Let's get Calc to write the code for us. So that'll be the next example. I'll be talking about a system called Fiat. And here's an example of that. So for this one, we need Calc 8.4 again. So here's an example of a specification in Fiat. Fiat is a general framework for programming with specifications and transforming them into correct implementations with good performance. And the example I want to use is, given a list of natural numbers, I want to compute another number n that is not in that list. Not exactly a grand challenge for verification, but a good small example to show this transformational program generation approach in action. So let's try that. So what I'm going to do, we generally prove lemmas that show how one term in this language, which is, think of it as a non-deterministic programming language where you're allowed to describe any mathematical set and pick an element out of it. And we'll gradually transform those programs from being entirely pick-based to being entirely algorithmic so we can run them. And one thing we can do, we can prove that any answer to the question, which number is not in this list, is also an answer to this question. Compute an upper bound for the list and then return something greater than the upper bound. So an upper bound is a number upper such that for every n that's in the list, upper is at least as big as n. And then one greater, an answer that is greater is an element of the set of beyond such that beyond is greater than upper. And this isn't too hard to prove as a refinement. So now we can reduce the problem to finding an implementation of upper and an implementation of beyond. So to implement upper, I'll use folding the max operation over the list. And I can prove that the max process, regardless of what we uses the initial value, where the 0 appears, will in fact give us an upper bound for the list. And that's not hard to prove. Here's proof. Then we can restate that property as a refinement. Namely, if you're looking for the set upper such that upper is greater than or equal to every element of the list, then you can Did I hear a question? Okay. Okay, then you can refine this into just returning the max element of the list. And that's just a simple wrapper around the property I just proved. We also need to implement returning a number that's higher than another one. That doesn't sound too hard. Let's just add 1. So we can prove that refinement as well. And now what I can do is, the overall problem is to find an f from lists to nats. It's in a comp monad. That is this language where we're allowed to pick elements of arbitrary mathematical sets. And I want to have the property that for any list, not in list of that list, refines into the application of the function we've generated to that list. So this is it's worth pausing here to clarify what's happening here. I'm using Calc's proof machinery, not just to show that a theorem is true, but actually to find a program paired with its proof. So any inhabitant of this type, any element of this set, is a correct implementation of finding a number that's not in a list. We don't need to write the program separately, though we sort of hinted at it by our choice of lemmas above. So in general, we're trying to refine not in list into some unknown h. What I'll do first is rewrite with our decomposition fact. And now we've reduced this to showing that this choose upper bound, choose beyond code can be refined into something. So we've sort of taken a transitive step in the lattice of refinements. And now I can use the property we proved showing that one way to find an upper bound is to get the maximum of a list. So when I run this list max refines, it's going to replace this whole set here with concrete functional code that finds an upper bound for the list, like so. Now there's a list max ls in that position. Then I'm going to use our increment refines fact. I have to use the setoid rewrite command that lets us rewrite underneath a binder. In particular, this is a binder for upper here, and I want to rewrite in here. So I'll use setoid rewrite. It's going to replace this whole set expression with a concrete functional program, like so, returning upper +1. And now we're almost done. We can make this program a little shorter by using the monad laws that tell you when you return and feed that right into a bind or assignment operation, you can just inline the thing you returned into all occurrences of the variable that got bound here. So monad simplification tactic does that. And now we need to show that returning list max +1 refines into something. Well, this is already a perfectly acceptable functional program, so I'll say we're done. Set h equal to exactly what already appears here. And now that we've done that, we have the proof, but we also have the program. So we can use this line to project the implementation out of the pair that puts the program together with its proof. And I can print out what we got, and it's this very reasonable functional program that just returns list max +1. And we can do some further processing to remove the return, so it is a standard calc functional program. The type even makes that clear without needing to inspect it. And of course, this program we can run and get answers on exciting inputs like this one. Tells us the number 14 is not in this list, which is 1 greater than the max in the list. Any questions about how that works? Yeah. Everywhere.
No, I mean, why do you need that? It's just the way that you like, I mean, you could imagine, I mean, this program, you could write the same program without having the model.
Yes, but in the intermediate steps of the search for the program, we had programs like this one that are a hybrid of functional code with picking from arbitrary mathematical sets. So it's a useful way to structure the search process. And both the spec and the implementation can inhabit the same type, so there's a smooth continuum between them that we can use during the search. Did that explain it?
A little bit.
Okay, yeah.
Can the specs actually run?
This cannot run, no. It's very easy to exhibit examples that solve undecidable problems. So we can't run them in general. Some of them, there might be heuristics to run. Any other questions about this simple version before I show a larger example of putting this machinery to work with more automation? All right, here comes the larger example. I'll open the bookstore. So we've defined some notations and definitions on top of the core Fiat library that let you get some of the same functionality we associate with SQL relational databases. Think of all the syntax I'll be showing you as desugaring into set theory. So let me start with the schema of a data store that our program is going to manipulate. So our data consists of two separate relations or tables in SQL terminology. This will be an example of an online bookstore, maybe, that maintains a database of books and orders people have placed for those books. Every book has an author, which is a string, has a title, which is a string, and it has an ISBN, a NAT, which is kind of a unique identifier. And there's a constraint saying that it really is unique. That's what this line means. And there's an orders relation that says for every order on a particular date, someone ordered the book with this ISBN. And we enforce that all the ISBN references and orders are pointing to actual books that exist. That's what this enforcing clause says. So again, this notation, imagine, is desugaring into set theory that describes the set of databases that are compliant with the schema. It does not explain directly what concrete representation in memory to use to represent the database. This is purely a specification construct. Fiat is going to choose the in-memory representation for us that makes things fast. So this is the data definition, and then we get to the actual operations over the data that we want to implement. So let's see how that goes. Well, first, here's the type signature of what we're going to build. It has a constructor that builds an empty database, and then operations to add an order to the database, delete an order from the database by the, not actually, that must be by ISBN or something, and add a book, delete a book. Most interesting parts are two query methods. One of them is going to get a list of the titles of all the books written by a particular author that gets passed in with this string. The other one is going to be, I think, also receiving an author name, and it's going to return a number that tells us all the total number of orders for books written by that author, which requires what's called a join in database terminology. You can also see all the methods have types that indicate they can do mutation. They take in the current database, represented by the unknown rep type, and their return values also include the after version of the database that incorporates whatever changes have been made. So let's see the implementations of these methods. I think I'll just focus on the query methods. Get titles is using this nice little query comprehension notation that says, how do we get the list of all the titles written by this author? Well, loop over all the books in the database, only keep the ones whose author field matches the author we asked about, and then return the title field for all of those. Then we also have this num orders method that's supposed to count how many orders for books written by this author. And this one does a nested loop over all the pairs of orders and books. It only keeps the combined entries where the book has the author we asked about and where the ISBN field matches between the orders and the books. And then we just return some dummy value. So think of this expression as representing a multi-set of answers, and then we use the count operation to compute the size of that multi-set. And that's the result of the overall query. The size of this multi-set is the number of orders for books written by this author. Any questions about this syntax or its meaning before I move on to compiling it? All right. In fact, let me start this running now because it's not the fastest thing around. So what happens when I run this? Again, I'm going to use a tactic. It's just a one-liner that is going to implement this for me. What that means is, one, analyze the syntax of the code, look at the pattern of accesses to the database, and choose data structures in memory to represent the database that will happen to provide fast implementations of the operations that this code uses. Two, actually generate the functional code for the method bodies that use those data structures to correctly answer all the queries and implement all of the methods that modify the database. So we have a general library tactic called master plan, name inspired by the idea of a database query planner. It takes one argument, which is essentially a plugin where you can tell it which data structures it's allowed to use. And the plugin also contains proofs of correctness for those data structures. This basic one here is just using nested binary search trees as the data structures, but we have other plugins for instance, tries for representing strings where you want to have efficient lookups based on prefixes of values. And in general, you can add any kind of data structure if you explain what it means relationally and then give some heuristics to decide when it's a good choice to use for a particular program. So it's kind of like an extensible database implementation where you can add new implementation strategies when you prove them. Yeah?
So does it also provide conversions between different formats? So say you write one program, it picks a certain representation, then later on and you put in some data and have that living in some database. Later on you extend the program to do small operations, and it figures out it might want to use a different data structure. Can you convert the existing database automatically into a new format as well? Or
No, we do not currently generate code for upgrading between versions of the program when you have changed data structures, but it's easy to see how that would be a valuable thing to add in the future. Let's see, how much longer do I expect this to run for? I think it's about a minute more. That's my feeling from running it before. Should have started this earlier. Anything else I want to point out here while I'm waiting? In the end, we're going to print a functional program, so we can all prepare our anticipation for that. Yeah?
So it seems like the most obvious advantage of this style is that it's sort of, you get to correct by construction implementations rather than writing a possibly bad implementation and trying to prove it.
That's true.
It's sort of like calculational style. What are some other advantages of doing things this way? Because you sort of still are writing the implementation because you're writing the refinements.
Yeah, but this is,
Right.
I didn't write it here. It's automatic. The idea is you abstract out implementation recipes that apply for many different programs in some domain, and you just keep reusing the same recipes. So it really is, another way to see this is as an extensible programming language where you can add new kind of programming notations along with their implementation methods, and it all works in a way where you're guaranteed that extension process can't break the correctness. You can think only about the original spec you wrote and you know whatever code comes out is correct no matter which extensions to the compiler were mixed together to make it happen. Yeah?
So we can know the implementation of this part, but can we know the implementation is efficient or human readable?
We can decide the question, is it human readable, by saying no. So we got that part. And is it efficient? That's just a heuristic question of the script you use to build it. We don't do proofs about that at the moment. Yeah.
So it's coming out defined, and it's presumably just checking that this is the equivalent of being on the QED. I'm not entirely clear on the difference between QED and defined.
QED makes the thing you've defined opaque. It hides the definition, whereas defined keeps the definition visible from the outside. I think this is almost done.
But we can feel fairly confident, since it's just doing the defined step rather than the other step, that it will do the good thing.
Right. In general, there need to be a tactic bug in Coq for this step to fail, unless it runs out of memory, which is definitely possible in general. It's not only checking a proof, it's generating a proof in a core format from the higher level tactics that were used. So it can be hard to tell how much of the time is split between those two steps. Yeah?
I heard that Home now has some option to run the technique in parallel. Have you tried that?
Have I personally tried it? I guess the short answer is no. Okay, great. Let's print a program. So let me skip to one of these queries and see what it's doing. I think there's still some more optimizations that could make sense to run here, but this is the lookup titles of books written by author method. At the inside, it calls a method on a primitive data structure that implements search trees, essentially, where we say lookup by this key S, and then we map over that, we map another function over that, and that's the answer. We could definitely fuse these two maps together. At some point we were doing that, but this version isn't doing it. And where do we see the data structure it chose? It chose to use a product of two different data structures, one for each table. That's not so surprising. And it made pretty reasonable choices for them. Each of them is a binary search tree with the appropriate key chosen based on which lookups need to be used in this program. Which lookup operation, being log time, would be especially valuable for this to be an efficient implementation of the queries that we asked for. And an interesting thing about the methods that add elements to the database is that they also include checks of referential integrity constraints. So there's an element of querying within the update operations as well, and that all gets generated automatically. So the next thing I want to do is show a little bit of the steps that are going on behind the scenes to automate the generation of this code. But are there any other questions before I do that? All right, I'll jump into it. So here comes bookstore more manual.v. So up to this point, same code. Let me just show what's going on in here. Maybe I'll start with this step. I'm not going to explain most of these lines, unfortunately, but sharpening is the word we use for the process of refining towards an implementation. So pretty soon we'll be looking at a functional program that looks a lot like how we might traditionally model a query plan in a database system. This choose indexes step is the one that syntactically analyzes the structure of the code and decides which data structures will be the fastest, and so that choice is now inlined into everything. And here is the first of those queries, the one that's going to look up all the titles of books written by a particular author. This is one implementation of that freely mixes functional programming code with mathematical set choices that aren't obviously computable. So what is it doing? This is basically just restating our query. The notation doesn't match exactly, but we're looping over the first table and we have a little where clause that enforces an equality for one of the columns of that, and then we return a projection of one of the columns of every such matching row. And then at the end, we have to pick a new database that is connected to the new database that the spec says is supposed to result. This is just like the crash safety examples we were just looking at, where there's a definition of the spec level state, and our job here is to compute the implementation level state. But that part of this is pretty straightforward for this example because a query doesn't change the state, so we can just reuse the old implementation state, and Tactics will figure that out for us. The first thing I'll do is I'll just use the monad laws to flatten some of the structure of this term. So now we get this big query-like for loop at the top of the program. So let's zoom in on just refining that query into something nice. So the first thing I'll do is notice that we're looping over a table. What could that be? Well, it turns out that looping over a table can be implemented by joining filtered lists, and this leads to a pretty long program. So what do? I think this first line is computing the cross product of all the tables we're looping over. And afterwards, we filter to just the ones that meet the condition that we're interested in. Here's a decidable test that popped up for implementing that the author field matches the one we're looking for. And something else happens down here. And here's the kind of projection element that returns just some of the columns. So one thing we can realize here that's kind of inefficient is we're first computing the full cross product and then filtering. But this is what's called a very selective query. It's only going to return a few rows probably. So we could save a lot of time by never materializing the full cross product. In other words, take the filter and push it inside the join process that creates the cross product. And by the way, in this case, it's a kind of degenerate cross product that just considers one table. So it's equivalent to just listing the rows of the table. So we have a tactic that distributes filters so they're inside of joins. And the result of that will be now there's a filter condition here that is part of the join filtered comp lists operation, which is, like it says, it combines cross product calculation with filtering to keep only certain results. This already is a big win. It'll give us a much smaller intermediate list than we had before. It'll only keep the list elements that are actually relevant to this query. And now we have a filter condition that is going to check whether elements of a list have the right string in a certain position. It turns out that instead of generating the list like that and sort of running through each element of the list and checking a filter condition, we can use our binary search trees to efficiently get the same effect by just looking up the right key in the first place. So we jump right to the list of elements we want instead of walking down a longer list and repeatedly running a Boolean test. And that's what implement filters using find will do for us. So the result here now is that we call the find method of our bag implementation that uses search trees, and we tell it just zero in on the elements that have this particular title or this particular author in the appropriate field of the table. And now this is essentially going to give us exactly the rows that we need. And I can make this look a little nicer by unfolding the definition, or at least make it more clear what's happening. Not necessarily nicer. There's a find operation followed by a map operation followed by a bunch of other stuff. But that actually, I'll hide again. Now let's run the monad simplification laws. So bring this down to the point where we're calling the method to find the list of all the rows that match this condition. And that's basically the answer, x0 that we can return down here, x0, where we then do some maps to fix it up into the appropriate form by projecting just the columns we care about. So then at this point, we have this unresolved requirement to choose a new implementation database that is related to the spec database. And easy to do in this case, pick new database figures that out. Now this is basically a functional program that gives us the answer. So we can say accept that as the implementation. And then similar things happen in the other query method that includes a join between two tables. Maybe I'll jump to this point where we use the same optimizations as I was using there. And I'll just show you things look a little different at this point. So here's a join with a nested join inside it that we run for every step of walking through the outer table. And we have a find operation on the inside that uses an index for an efficient lookup. And then a bunch of mapping happens at the end. And then I've expanded out a bit of the simplification with monad laws here. And we can just run these and see simplification happening. And so this should wind up flattened pretty much. You can see here is where the rewriting process, at least in Calc version 8.4 that this is using, can be a significant performance bottleneck. Even one of these rewrites takes long enough to notice. And we reduce everything to calling an enumerate method on one of the tables and then looping over the contents of another table where we're, on every iteration of that loop, calling a find method on the other table and combining things appropriately. And that one we can finish in the same way as before. And in fact, like I showed in the first version of this code, we have tactics that will automate that whole process. So I'll just call those to finish off all the other methods that I haven't been focusing on here. And then, almost there. Any questions in the meantime while these few lines are finishing running? Yeah?
So is a correct characterization of this Fiat is a library for writing correct by construction compilers to Galena from a specification language?
That seems like an accurate description of at least a big part of Fiat. It's also a library for writing the specifications in the first place.
Could you repeat the summary?
The suggestion was, one way to think about Fiat is a library for building correct by construction translators from specifications into Galena. And that is indeed the bulk of what Fiat is about. Almost done here. And I'll just do a few more optimizations, and I'll rewrite the program where it's just obvious that every method body is just returning a value and not using this possibility to pick elements of arbitrary mathematical sets. And that is going to be the final answer. So a few optimizations happen there. So let's see what determinize is doing. We still have methods that include operations like this one that are not obviously rets. So let's see what determinize does to that. All right, did that get better? It's definitely created a lot of indentation that makes this harder to see. But I just skip to the end of this. And we can take a look at the program that popped out. It should be the same as before. It'll probably take a few minutes for define to run, so it should be ready just at the end of the lecture period. Any more questions in the meantime? Yeah.
So you've shown us like 3 frameworks that employ automation in order to produce things, and they really seem to
I have one short answer and one glib answer. I'll do the short answer first. Start doing things manually, and as you notice, repetition, abstract into automation, and then use that instead. This process iterates, and you're gradually raising the abstraction level and building automation whose primitive building blocks are whatever the building blocks you'd come up with for the previous layer. And as you repeat this process through experience, figure out which automation is effective, you'll gradually build up to the big hammer tactics that do most of your proofs for you. The glib answer is, the question is sort of like, so how do you go about designing and writing programs for new tasks? There isn't a simple answer. It's a whole art that depends on experience and learning about design patterns, and resists easy summarization.
By the way, we're finished.
Thanks.
How long did it take you to design each one of these libraries?
Varying answers, but upper bounded by a few years for each one. So now this popped out, and it's the same code we saw before. And each program is pretty obviously a functional program. In fact, we don't even allow any of these funny pick from set operations anymore. So I can take another question or two, the remaining time. Anything bigger picture about the subject of automation along the lines of the last question? Yeah.
Do you have any general tips for writing tactic scripts that don't just say they failed, but like leave you in a state where you can do the harder cases by hand or see the harder cases?
Right, and indeed, all the ones I demonstrated here have that property.
Yeah.
So the glib answer there is write them that way. Set them up where if there's a point where you could fail or return a subgoal, return the subgoal. Usually most search strategies make that pretty easy to do without extra effort. I don't know if there's a general recipe that makes that easier than thinking it through for each case. Yeah.
So, kind of to follow on that question, this was what was applying partially to my question yesterday on what if we had whiles in an INT program.
Okay.
Because the automation that we had there with the reflection, if there was a while anywhere, would just fail and it would not do anything useful. Whereas I was starting to think in my mind, could we have written a tactic that, say you had something sequential and then a while at least process the initial sequential part?
Yeah, we can imagine doing that. Where the symbolic evaluator returns a residual program that it didn't know what to do with, and you have to run that yourself somehow.
And so that was a property that reflection technique didn't have yesterday.
That's a fair criticism, yeah.
How much machinery did you reuse in between all those projects?
Not too much, just some utility libraries about things like extensible records and similar stuff you could imagine moving into the Coq standard library. Yeah.
So following this question about the design of these automation things, do you have a hint where to draw the line between I just prove a lemma or I automate the full process of proving that something?
I don't have a short, ready answer for that question. But a lot of it has to do with performance and readability. Lemmas are nice because they have documentation value. You sort of have to decide what path you want to lead the reader of your code down every time they encounter it. And yeah, it's sort of like asking, how should I divide my program into functions? It's a hard thing to do nicely in general, and we're all still learning about it as we write more programs. Yeah.
What do you think of using tools like FStar or definitely in a project like Bedrock? Will it be possible or will it be hard?
Well, it would be a very different system if implemented in one of those frameworks. And I think in general, FStar, Daphne are much harder to learn to use for advanced cases and easier to learn to use for simpler cases. When you get stuck with one of those, you're really stuck. And you're really stuck. You have to go ask for changes to the implementation of the tool. Whereas with calc, you can prove whatever true thing you want with enough work. You don't wind up stuck in the same way. All right, I should probably stop here. So thanks. Enjoy lunch.